Yeah? Okay, we can start. Thank you. So, yeah, welcome to probably the last lecture of module 1 this week. Yeah. So before I forget, a couple of announcements. The assignment is due on Friday at 10 a.m. 14th August. The top deadline is 11 a.m. And I think the TAs have posted the submission guidelines in the WhatsApp group description as well as on Piazza. So please follow those instructions and submit by the deadline. Submitting assignments is essentially mandatory in my courses. So if somebody does not submit, you will receive messages from some people on the WhatsApp. And assuming we finish module 1 today, or maybe another ways, most likely tomorrow, which is Thursday, and the last lecture of this week, most likely we will do introductions. So typically, almost all my LP courses, there will be one lecture where we do introductions. I don't put it in the beginning because some people drop out, some people add, etc., etc. So typically, I do it around after 1 or 2 weeks. Right? And that also helps in finding collaborators, of course, because the top deadline is so early. This will not help you probably in finding a collaborator for assignment 1. Because the introduction will be tomorrow and the deadline is the after tomorrow. So hopefully you will not benefit by tomorrow's introductions for finding a collaborator for assignment 1. But maybe if assignment 2, you don't have to have the same collaborator. And if you do not collaborate on assignment 1, you can choose to collaborate on assignment 2. So the introduction will hopefully also help in case anybody is struggling to find collaborators. Okay. Okay. Are there any questions, concerns regarding anything we have discussed so far? No? So shall we jump right into the match? Yeah? Alright, so quick recap. Right, so we are looking at the shortest path problem, also known as shortest ST path problem. And there is the optimization version, which is wanting to find the shortest path given to its SME, and a cost function on the edges, which is also known as a distance function, which is where the terminology shortest comes from. Right? And of course, if there are no costs, you can assume that the cost of every edge is 1. That is the same as the cardinality version. So that the cost is just the length of the path, which is the number of edges in the path. And of course, there is the decision problem for both the cost and cardinality version. I'm getting now the cardinality version. So given a specific ST path, you want to decide whether that is a shortest ST path amongst all ST paths. And so clearly the problem is in ONP, because if it is not, the certificate is just another, clearly the problem belongs to ONP. And what we were discussing, I mentioned that the problem also belongs to NP, but we will just try to convince ourselves for this particular graph. I think the path that was proposed was S13P. And the claim is that this is a shortest ST path. So this is the path P. Right? And the question is, how do we convince ourselves that this is indeed the shortest ST path? So one TII from last time was to basically use this proposition, observation, the graph, SNP distinct vertices, and if you have any ST paths, and let's say you have an ST cut, then we observe that they must meet at least once. So P viewed as a set of edges, intersect the cut, which is NP as a set of edges. There is non-NP, therefore at least one. Yep. And so can we use this proposition for this example? Find a collection of ST cuts that would basically prove that this is indeed a short SSD path. Anyone? Okay, then we find a collection of SD cards which will have the property that we want. Yeah.
Can take 3 separate class.
3 cards. Okay. Okay.
So-
And what do you mean by separate? Can you specify that?
The pair disjoint.
Yeah, you're going to give 3 pairwise disjoint. Pairwise disjoint SD cards.
Yeah.
Okay. So the narration. Okay. So the idea is, if we can locate three pairwise disjoint SD cards, pairwise disjoint. Right? So an SD card is a set of edges. So the intersection of LP is empty. But then it would follow from this proposition. Can somebody say what would follow? That an SD path must have at least 3 edges. It must use one from each of those cuts. And because they are pairwise disjoint, it must have at least 3 edges, and then it will be done. Yeah? All agree? So if we can do this, then we are done. Right? Because this path has length 3 edges. Yeah? So now this should be pretty straightforward to locate such cuts, right? Especially when the graph is drawn nicely, cuts also look nice. I'm really drawing. It's not as easy to see that. Right? So maybe. Okay, so maybe somebody can do one cut. Somebody else maybe. And then someone will propose a cut that can be extended to family lenses. Yeah, can you get what?
S.
Partial of S.
And then
Okay, somebody else. So partial of S is one cut.
partial of
Okay. Partial of
S01.
S012. Okay, S012. And Rita? Partial of T. Yeah, that's 3 cuts. One comprising 3 edges, one more comprising 3 edges, and this fellow comprising 4 edges. So observe that they are pairwise disjoint. Is that correct? There is no common edge between any two. Is that right? Together? So this collection of cuts implies that this is indeed a short SSD path for this particular. So let's see. So I call this collection script C. Collection of if you can look at I will use color here, script C. Okay. And then the conclusion is that the length of any SD path is at least okay. Of course, previously for this example, this doesn't prove anything in life actually. Only for this example it proves. Right? But the point is that if you could show that for any graph there exists an SD path P, right, and a collection. So observe the following. This is if for a graph G there exists an SD path P and a collection strip C of pairwise disjoint SD SD cards such that their cardinalities are equal. Such that the cardinality of P, right, which I am referring to the number of edges in P, is equal to the cardinality of C. Then it follows that P is a shortest sequence. Actually, let's take this a step further. Instead of SD paths, which is the problem, which is the primary problem we are focusing on, let's consider this secondary problem: collection of pairwise disjoint SD cards. This also leads to a problem, actually, an optimization problem. Would you like to minimize such a collection or maximize? What would be interesting? Is it interesting to minimize or maximize? Maximize, right? So one could ask the following question that arises from this observation. What is the largest cardinality of such a set? Right? I mean, I don't see a real world application to do this. Shortest path is clearly more real world. You go to my home, blah blah blah, 2 million maps. Right? But anyways, you see that this is also an optimization problem, right? Try to find a collection of pairwise disjoint SD cards that is as large as possible. There's an optimization problem hidden here. What can you say based on this observation? If this is true, then what does it mean? P is the shortest SD path, and somebody
is the biggest.
and script C is the largest collection. Right? Not only does it imply what we wanted, it implies something more, right? And P is a shortest SD path, and in fact, script C is the largest such collection. Right? And here we use the fact that for any SD path and any collection, the cardinality of P is at least is at most this. No, is at least. So if I define 3, then the length is at least that. Yeah, this is true. And therefore, if these are equal, then this fellow is as small as possible, and that fellow is as large as possible. This is already a glimpse into UI. But I'm more commented to that setting. But these kind of things will keep happening throughout this course. Okay? This is basically the first place where we are seeing glimpse of UI. Okay. But anyways, so of course we haven't proved at this point that the problem is in NP. What we will see by module 4 is that this always exists. So we don't need the chief case here. We will see eventually that this always exists. In any graph, there is always an SD path and a collection of pairwise disjoint SD cards such that the cardinalities are equal, and that is a certificate that the given SD path is indeed the shortest SD path. Yeah? So therefore, when we do that, it will follow that the problem belongs to NP. In fact, we will see a stronger version of it. We will see the weighted, or if you like, the costed version of this when you have costs. And if you put all costs equal to 1, you'll get this as a corollary. Okay. Any questions, concerns? Good so far? What I want to do next is I want to continue focusing on this observation, which is the primary thing we use here, in order to now formulate an integer linear program for the shortest class, So, natural question, what should our variables be? And based on the discussion, I think it's fairly clear by now that we need a variable for each edge. Because we are viewing a path as simply a set of edges. So we do that and have a variable for each edge. These are often called indicator variables because of the way we interpret them. So I'll call them indicator variables. So let's say the variable is FC for each edge E. And the interpretation is the standard interpretation. We want it to be either 0 or 1. 1 means it is in the path, 0 means it is not. That's sort of what we are looking at. Or at least in some sense we call this the ideal interpretation. We'll see why. So x equal to 1. We should interpret this as E belongs to the class P, where P is our desired shortest path, and x equals 0 will be interpreted as B. Good. Let's focus on let's get done with the objective function. That's generally the easiest part about these things. So what are we trying to minimize? Supposing we are given costs on the edges, real number, non-negative real numbers. What are we trying to minimize? Minimize? Some cost of the path, which is summation C. Right? So what is easy is this is what we are trying to minimize. Always there was 1 point. Sometimes I will write CE, sometimes I will write CE. Means okay, so that's what we are going to minimize. We are going to minimize the cost of the two images. What is much more interesting is to figure out the constraints. Right, so it's something that clear based on our interpretation. We want these variables to be non-negative. And we want them to be integers. And since you are minimizing, that should basically take care of this. So let's just like that. We want the x's to be non-negative, and we want the x's to be integers. And because you are minimizing, unless the cost of an edge is 0, you won't set xe to be too positive. And of course, there are written down of constraints, but that is sort of the idea. The big question is, what are the main constraints? What constraints will force us or will ensure that the solutions to the system are indeed shortest paths or not shortest paths, RSC paths. And the optimal solutions are shortest system paths. And that is what we want. So the main thing is to formulate constraints or impose constraints so that, so ideally what would happen is all solutions will correspond to STRs. Any solution to the system, which means anything that satisfies all the constraints. Solutions correspond to ST paths. And of course, since we are interested in optimizing, what is perhaps even more important is that optimal solutions, and here of course by optimal we mean those that attain the minimum because it's a minimization law. Optimal solutions correspond to shortest ST paths. That's what we ideally want. Yeah? So how do we make sure that we get these two things? Okay, maybe raise hands and maybe you can write down constraints in your notebook. I don't know.
Have two and maybe not go.
Yeah, so this is actually crucial. Even if you don't get both, but you get one of them which is more important, that's good enough. Which one? Let me say. And if you don't like this, ideally word, just assume all costs are positive. Then you don't even need this. Either or assume that all costs are positive. See the function from the edges to the positive reals. Going away. No, even that will not such a good problem. Even then, yeah. Let me not write all. If you like, you can assume this. If you find this zero cost annoying, just throw a zero cost. Okay. See if there is something based on the proposition. Something based on issues. So it looks like a lot of you, based on the folks I've talked to so far, are trying to capture the problem exactly. So what you are trying to attain is the ideal, right? So you are trying to attain a situation where the solutions will be exactly the ST paths and the optimal ones will be precisely the shortest ST paths. One way to do it is to think of a path. What does an ST path look like? It starts at S, ends at T, and but of course the graph may have more vertices. And so one way to think about the possible formulations is to look at this figure and focus on the degrees of the vertices. Right? So what are the degrees of all the vertices? So S and T degree is 1 in this yellow graph. Only the yellow is picked. And the degree of every other vertex is 0 or 2. So that leads to a very natural formulation, which is that for if you take here this instrument at S, this is shorthand for I think we discussed it before in matching this. This you want to be equal to 1, and you want the same thing for T. You want that to also be equal to 1. And for every other vertex, you want it to be 0 or 2. So, for a vertex that is not S or T, you want this to be either 0 or 2. So, this is a kind of constraint some of you have written. For all V in the vertex set, minus S minus. So, I'll just go. Let me just go over the things. So yeah, that's what some of you have written, right? But there is an issue. Is it an ILP? Right, let's go back to the definition of integer linear program. An integer linear program is first of all a linear program, where a subset of the variables are required to be integers. So you are allowed to impose the integrality constraint. The integrality constraint looks like this. Right? You can just say, I want blah variables to be integers. But you cannot say, oh, I want them to be 0 or 2. And that is not allowed in an ILP. So that's one issue. If this is the formulation you are going for, that's not an ILP. Right? In other words, if I drop the integrality constraints from that subset of variables, I should get a linear program. So that's one issue with this formulation. Yeah. Okay. Yeah. Yeah, so some of you are saying that you might still be able to salvage this. Yes, it might be possible. So see if you can somehow still salvage this, I'm not sure. Yeah, but again, this is not the formulation I'm actually going towards, but that's okay. If it is a valid formulation, this is a valid formulation. What we are going to be interested in eventually in module 4 is whether we can use the formulation we have to get an algorithm to solve the problem. That's a separate point. Right? So right now we are just focusing on formulations. So, yeah. Okay. Okay, so maybe we can continue discussing this one on Calza. If anybody can get an ILP using the same kind of ideas, I'd be very happy to see that. In fact, this was the same formulation that was proposed in 2022, and even then I did not know whether we can convert this idea into an ILP. Maybe it is possible. But what we will do next is we will see a different way to write up an ILP based on this proposition. Right? And it will not attain the ideally thinking. That's okay. So, notice that this is a minimization problem. If you give me a set of edges and you tell me that any ST path within this set of edges is the shortest ST path, then I am happy actually. If you just give me a set of edges, so you don't, you basically just pick the variables that are equal to 1, right? And I'll take that set of edges. What I'm saying is it may not be an ST path, but it may contain an ST path. That is probably good enough. And if I look at the optimal ones, then because our costs are non-negative real numbers, if I have an optimal solution, even if it has more edges than an ST path, that is still okay. Those edges will just be zero cost edges. Because if they were not zero cost, then an optimal solution would not have picked them anyways, because a subset of it has an ST path. So if I have a shortest ST path as an optimal solution to the ILP, right? Potentially zero cost edges, I could still add them, but they don't really bother us because I'll just find an ST path in the given set of edges. So that is sort of what will happen when we see the final formulation. Right? So what will happen is, instead of having an ST path, the solution will be ST paths plus more edges. And the optimal solutions will actually be shortest SD paths plus more edges, but those will be zero cost edges, because if they were not zero cost, then they would not be an optimal solution anyways. So that is sort of what will happen, because we are going to use this very weak proposition to formulate the ILP or an ILP. Yeah. So now can people think in this direction? Can we use this to formulate an ILP? And I'm going to give you a DIY, which I probably should have given last time, but I forgot, which is related to this point. And it's related to understanding cuts better. How do you define a connected graph? How do you define graph being connected or not? Is there a way to define using cuts? Okay, so this is a do it now. Is that right? Complete the following statement. A graph G is connected Connected just means, in some sense, for two specific vertices, either there exists a path or there does not exist a path. Right? So, SLP belongs to the same component, it cannot be blah blah blah. That's very good. A graph is connected if and only if some statement about cuts. How do we define a connected graph using just cuts? Okay, and if you're done with this, then how would you define the existence of messy paths using just cuts? There exists a messy paths in the graph G if and only if some statement about cuts.
You have to qualify. You are right. You just have to qualify. No, but before that, can explain this. Can everybody say some conditions possible? So you need necessarily sufficiency of transparency.
Suppose you have seven lines. First one we will have E1, E2, and this one we will have E2, E3, E4. E2 can you have it's a common application.
It's not easy. So you're given a unique testicles, which is so we are saying that you could also make something this is the time to But we are trying to see the existence of the value. We are not trying to say given consent.
Okay. So I think a good number of you have figured out this one. And general answer seems to be as follows. Graph is connected if the empty set is not a cut of the graph. Something like this. Which is almost true. The problem is the empty set is a cut of empty graph. Because it is a partial of empty set. And we never said, when we defined cuts, we never said X is a non-empty set. And we said X in any subset of the vertices. Therefore, it will be the empty set, it will be the whole set of vertices also. And both of those will, of course, give you the empty set as a cut of the graph. But apart from these two, the empty set is not a cut of the graph. That's what you want to say actually. And one way to say that is if you take any non-empty proper subset of the vertices, for all X that is not empty and is a proper subset of the vertex set of the graph. Now the corresponding partial is not empty. So this is what we really wanted to say, which is that basically the only way to get the empty cut is to take the whole set of vertices or take nothing. Otherwise it won't be. And this is pretty straightforward to see pictorially. And if I have a component in the graph and there is another component, look at the cut corresponding to this component. There are no edges coming out because it's a component. And anyway, you can write down a formal proof. So it is pretty straightforward. So now it is a DIY. Write down the proof. Yeah? You all agree with this statement? If you take any non-empty proper subset of the vertices, there will be some edges leaving that set. That's all it is. And this one, you can write this in terms of ST cuts. An ST cut is already quite nice because S is here, T is here. So therefore, both sets are non-empty proper subsets of the vertex set. So that's already nice. And if you want an ST path to be there, you want at least one edge in the cut. Right? In fact, what is true is there is no empty ST cut in the graph. There does not exist any ST cut that is empty. No matter how you split the vertices, S is on one side, T is on the other side, there will be at least one edge going from the left side to the right side. So now can we use this or equivalently this in some sense? Although this is just one direction, it's just saying that MVST path and ST cut else. Can we now see how to formulate constraints? Can you come up with a constraint that will basically guarantee that any solution that satisfies those constraints, integral solution, will contain an ST path? Let's forget exact correspondence to ST paths. Can we at least make sure that every solution will contain an ST path? And then because we are minimizing, the optimal ones in some sense will be exactly the shortest ST paths. Especially if you throw away zero cost edges, they will be exactly the shortest ST paths. So what can you now constraints now? You can kind of see where we are going, right? We want a constraint for every ST cut. So we will write one constraint for every ST cut. If you are worried about the number of ST cuts being exponential, don't worry. Definition of ILP just requires finitely many. So right now we just formulating ILP. So it's okay to have exponentially many constraints. It's okay. So long as it's fine. Okay. So for every ST cut, we are going to have a constraint. And these things are basically suggesting what the constraint should be. We want to make sure that from every ST cut, we choose at least one edge. Right? If we choose at least one edge from every ST cut, then we all agree that such a set of edges will contain an ST path. In the proof, we'll write it down. So for every ST cut, for each ST cut, partial of x let's put the following constraint. Oh, I don't like partial x, that's not sorry. It's not okay. I'm just going to call it cut C. Okay? C is just, it's a set of edges, so you can think of it as C as partial of set. But yeah, these are used to different x's. So yeah. For every edge in the cut, we want, yeah, if I sum up all the x's, that should be a prism. For every ST cut of the graph G, right, we are going to have the inequality that at least one edge is chosen. right? Because if they are integers, then that's what we do. I claim that all solutions to this system may not be ST paths, but they contain ST paths. LP solution contains an ST path. What do I mean by this? A solution is a setting of the variables to integers that are non-negative. So the variables could be 0, 1, 2, 3, 4, so on. That's one problem. They are not necessarily 0 or 1, unless I put XC at most 1. If I put that, then yes, there will be 0 or 1. But if I don't put that, then they could also be 0, 1, 2, 3, 4. That's okay. Because in a minimization problem, if the cost of an edge is positive, you won't set the XC variable to be more than 1. If all the constraints are satisfied by setting it equal to 1, then there is no reason to set it equal to 2. So, that's one point. So what we will do is, by what I mean by contains, I will take the ones that are not 0. The ones whose variables are greater than equal to 1. Right? I'll take those edges. And I claim that this set of edges will contain an ST path. Okay? So by contain I mean XE at least 1. We are going to change the interpretation. This was the ideal interpretation. So let me make this at least 1 now. Okay. If the variable is at least 1, I'm going to interpret as the edge belonging to B. Otherwise, it will be 0 because they are integers. In which case, it's not B. And now, I don't need contain. Now, if I interpret like this, let me not call it P because P looks like a path. Let me make it Q. Yeah? So then my solution Q will contain an ST path P. That's one thing. Every solution interpreted this way, take those edges, it will contain an ST path. And the optimal ones are the ones that are minimizing the cost. They will contain an ST path. In particular, shortest ST path. And can they have any more edges? Yes, they might. But those edges are 0. They are 0 cost edges. So optimal ones are just shortest path plus 0 cost edges. That's okay. In particular, if there are no 0 cost edges, they are shortest paths. Right? So the optimal ones will be shortest paths plus potentially extra 0 cost edges. This is what we have. Yeah? Okay? We haven't proved anything. I'm going to give our proposition as a DIY and we'll probably prove it tomorrow. But it's really pretty straightforward. It's not difficult. So here's the proposition. It basically captures this thing. It's just data inside the G is the graph. S and P are distinct vertices. I'm going to take a set of edges that intersects every SD cut. That's basically the constraint reality of it. That FB, a subset of the edge set, such that F meets, intersects every intersection of monoids, meets every ST cut of the graph G. Take any set of edges that meets every ST cut. Right? So the intersection of every ST cut should be non-unique. Then my claim is that the following graph, you take all the vertices of the graph G and you take only the edges of F. This subgraph. Okay, I'm only taking the edges of F. Then the claim is that this fellow contains an ST path. If you take any set of edges that meets every ST cut in the graph, this already implies that every ST cut is non-integral. Otherwise, all the intersections. So, this is a TIY. We might write down the proof of this tomorrow, but it's pretty straightforward. I think you all should be able to do it yourself. And this is basically the reason why this thing goes. This one is probably just really good stress on it. Okay. So this is going to be the ILP we will be using for the shortest path problem. Because this ILP in particular, there is a very nice way to get the ILP problems. Of course, that doesn't mean that other ILPs are useless. Maybe the other ILPs are also lead to nice algorithms. I don't know. Okay, so that's the ILP. One more small TII for tomorrow. Convert this into matrix vector notation and define the matrix as you like, as required. Right? Oh, very good. This is part of the ILP. Okay, so TII. Convert to compact form, which basically means using vectors and matrices. As we noted, or as you probably can see, the number of ST cuts is exponentially many. Right? So there are an exponential number of constraints. There is one big difference between this ILP and the perfect matching ILP. The minimum cost perfect matching ILP. You know, there is one difference. That was one constraint for every vertex. Right? That's n with n number of vertices. Here you have an exponential number of constraints. The other big difference is the perfect matching ILP captured the perfect matching problem perfectly, if I may. Right? Whereas here, it is slightly imperfect. Yeah, that's the other difference. Someone reminded me, maybe it was Gautam, that I haven't defined stable sets yet. So let me do that in the next 5 minutes. Because it is on the assignment. Is that right? It's on the assignment? Okay. So, of course, let me not make it sound discontinuous. So the two combinatorial optimization problems to which you will see sort of exact algorithms that solve them exactly and in polynomial manner are the shortest path problem and the minimum cost perfect matching problem. But of course, there are other combinatorial optimization problems, and some of them are not as friendly as these two. One such problem is coming from stable sets. Let's compare this with matchings. Right? So what is a matching? It is a set of edges. It is a set of edges such that no two share a vertex. Is that what I wanted to say? Yeah. It is a set of edges such that no two of them share a vertex, which means that they are not, no two edges are adjacent or sort of incident with the same vertex. Stable set is very similar in some. Instead of a set of edges, it is a set of vertices. It is a set of vertices such that no two share an edge. Okay, that's what I write. Any subset. What's this stable set? It's any subset S of the vertex set such that no two are adjacent. That's what I would say. Another would say it is no two share an edge. By sharing an edge, the edge should have both as ends. Okay? So you already that it sounds pretty similar to matchings. Right? And just like in the case of matchings, what would be interesting? Minimizing or maximizing? Maximizing, right? Empty set is a stable set. Oh, by the way, this is also called independent set. The CS folks call it independent set, math folks call it stable set. My choice is right. So the interesting question, an optimization problem. Given a graph G, find the stable set of maximum current value. Find a maximum stable set. Right? Sounds very similar to the maximum matching problem. The maximum matching problem is polytime problem, as you will see in this course. Belongs to NP to NP, everything given. This problem is NPR. We don't know how to solve this efficiently as of yet. And unless P equals NP, we don't expect to have an efficient algorithm for this problem. Right, so this one is a stable set problem in NPR. And if you write down a decision version appropriately, you get an NP complete problem. Yeah, anyway, I don't want to go into formal definition of NP hardness and NP completeness. The point is that this is not efficiently solvable unless P equals NP, which people typically don't believe. Right? So that's the big difference between these problems. So we will not see a solution to this problem. We will not see how to efficiently solve it, since we haven't reached there yet as a species. Yeah. Okay, questions, concerns? So anyway, so that's the definition of a stable set. And it appears on your assignment, so I should cover it. Thank you very much. Anything else that I've missed that is on your assignments? Is there anything else that feels like it should have been defined but it is not defined? If there is anything, please let me know tomorrow, because the assignment is on Friday, so I will at least define it tomorrow. But hopefully it is in this. Okay, so that's all for today. And I'll see you tomorrow at 3:30. We will quickly finish module 1, the few things that are remaining, and then we will start introductions. Right? So please attend and participate. We will not record the introductions, of course, but we will cover the rest if there is any. Thank you.